All right, we're going to look at a little bit what happens when you actually start taking into account the wave properties of light. We've mostly ignored the fact that wave is a light as it goes through reflection and refraction. Those properties don't explicitly depend on the wave nature of it, but interference does. All right, so let's look at a way to represent light. What we're going to do is have light moving out either as circular wavefronts or straight line wavefronts, where the direction of motion is one way, and because light is a transverse wave, what I'm going to do is show maximums in either the electric or magnetic field with these lines here. So the midpoint in between these lines is where you get, the exact opposite. So we're at the top of the sine pattern, bottom of the sine pattern, back to the top. All right, because we're going to look at how these waves interact with each other. And waves, like anything else, can add up because it's made up of electric and magnetic fields. So if you have two light rays, depending on where in their wave pattern they are, if they're in phase or out of phase, you can get them where they add up and get brighter, or they cancel out and get dimmer. All right, so we'll be looking at interference patterns between bright and dark. All right, what happens, it turns out, when you have light passing through some kind of opening or aperture, it starts to bend as it goes through. That's called diffraction, which we'll talk about next time. What happens, it starts to go through there, and then you can get overlap of two different ones. So we're looking at one of the first experiments that proved that light was a wave. It's called the double slit experiment. So you have two slits, the light passing through, and in some places it'll overlap at a maximum, in some places it'll overlap at where there's a maximum and a minimum lined up. So what happens, we have these two slits, and there's a wave kind of going to some point P at different points in space. So what we can do is we have the two sources. If their waves line up, the superposition of those two waves, the addition of those two waves, you get a bigger wave. All right. And then if they're out of phase, where you have minimum here lined up with the maximum there, you get a superposition of 0. They cancel out. So this is what's called Young's double slit experiment. And what you can do is have different wavelengths of light going through double slits, and then showing that blue light and red light have different wavelengths, and that directly that they are waves. Okay, so what we have is the light source going and hitting these two slits. So along here, when you have all the waves adding up, there's some places where the maximums all line up, and that'll give you a bright spot. And then in between, you'll get dark spots. So it's kind of alternating bright and dark. So we're going to say these slits are separated by some distance d, and if we look at it, there's some angle going from the center up to wherever we're measuring. And if you look at it, these two paths, the top portions here are the same, but the bottom section has this extra amount to go. And if we want that to be constructive interference, we want that to be either equal to the wavelength, or 2 times the wavelength, or 3 times the wavelength, so that it lines back up. So you get those sine waves kind of shifted over, and so you get bright spots here. If it's shifted so that you get exactly a dark spot, it'd be half a wavelength, 3 halves, 5 halves, so that you're exactly off, and so it'll start canceling. So for constructive interference, that path length difference, we're going to call that delta, this difference. So it's the difference between the two paths. That ends up being the distance between the two slits times the sine theta. Let's go back here. So d sine theta, so opposite hypotenuse. And we want that equal to some number of wavelengths. So m is just going to be a number. 0, 1, 2, 3, blah, 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 or positive or negative. Positive goes up, negative goes down. Sine is positive up, negative down. So what's happening there, we're having it offset by some certain number of wavelengths. Okay, destructive interference, where it's half numbers of wavelengths. 1/2, 3/2, 5/2, something like that. So you're going to be doing m plus 1/2 lambda. So it's the same conditions, except you have this plus 1/2. And then if you look at really small angles, less than, okay, I need to figure out what's going on here with my mouse. If you have angles less than 4 degrees, really close in, and what you do is, when this is really, really, really far away compared to the size of these apertures, what happens, tangent of theta is just y over L. And for small angles, tangent of theta equals sine of theta, and we can say that equals theta is y over L. And so if we take that condition for maximum d sine theta is m lambda, that becomes y equals m lambda L over d. So we'll be using that a lot. So this is a nice condition to use, but this is our main condition. Both of the top one is always true. The bottom one is only true for small angles. So these are some of the variables we're going to be using. All right. Well, thank you very much for watching, and there'll be one more for part of this unit.